Why China is building giant particle accelerators to print 1-nanometer chips is one of the most misunderstood stories in the global technology race. China just completed the world's most powerful synchrotron light source, a particle accelerator the size of 90 soccer fields that generates X-rays 1 trillion times brighter than the sun. It cost $665 million and took 6 years to build. $665 million more than the GDP of some small nations, spent on a machine that bends electrons around a 1,360-meter ring at near the speed of light to produce light no other technology can replicate. Let that scale sink in. And it is not the only one. To understand what China is actually doing here, and why it threatens the Western semiconductor establishment in ways that export controls were never designed to prevent, you first need to understand what these machines can do that nothing else in the world can. The light that sees inside atoms. Before you can understand what a synchrotron does, you need to understand what light actually is, and why the light we use every day is almost completely useless for the problems that matter most in chip manufacturing. Visible light has a wavelength between 400 and 700 nanometers. That is the range of colors your eyes can detect, from deep violet to deep red. When engineers use light to etch circuits onto chips, the fundamental process that has driven 50 years of semiconductor progress, they have been fighting against one unbreakable physical constraint. You cannot reliably pattern a feature smaller than the wavelength of the light you are using. This is called the diffraction limit, and it is the wall that every generation of chip-making technology has crashed against and had to find a creative way around. Extreme ultraviolet light, the light that ASML's most advanced machines use, has a wavelength of 13.5 nanometers. That is the frontier of commercial chip-making today. At that wavelength, you can pattern the transistors that go into the most advanced chips on Earth. TSMC is using it right now to produce 2-nanometer chips. But here is the thing that changes everything. Hard X-rays, the kind produced by a synchrotron like HEPS, have wavelengths between 0.1 and 1 nanometer, that is 10 to 100 times shorter than EUV light. And the shorter the wavelength, the smaller the features you can theoretically pattern. At sub-nanometer wavelengths, you are operating in a regime where 1-nanometer chip features are not just possible, they are physically within reach, in a way that no EUV-based system can approach. This is not a new idea. X-ray lithography has been understood as a potentially transformative technology since the 1970s. IBM, NTT, and AT&T Bell Labs all ran serious X-ray lithography programs in the 80s and 90s. Synchrotron radiation sources were built specifically for semiconductor patterning research. Researchers demonstrated resolution down to 15 nanometers using synchrotron-based X-ray lithography years before EUV was commercially viable. The technology was real. The physics worked. So why did the semiconductor industry choose EUV instead? The answer is not that X-ray lithography failed. It is that X-ray lithography was harder to scale, harder to control, harder to make economically practical for a factory running millions of wafers per year. It requires one-to-one masks. The mask is the same size as the features being printed, rather than a reduced image projected through a lens, which makes mask manufacturing extraordinarily difficult. And synchrotron light sources, at the scale needed to produce the intensities required for practical lithography, were too large and too expensive to build into a chip factory. But then came something that changed the calculus entirely. The machines that were too large and too expensive to put in a factory, China just built 4 of them. 4 machines that should not exist. In 2025, China achieved something that no other country has done. It completed a cluster of 4 interconnected photon science facilities in Shanghai's Jiangjiang district and Beijing's Huairu Science City that together form the most powerful concentration of particle beam light sources ever, assembled in a single national ecosystem. To understand what that means and why it matters for semiconductors specifically, you need to know what each one of these machines actually is. The first is the Shanghai Synchrotron Radiation Facility, the SSRF. Operational since 2009, upgraded through 2023, it is a third-generation synchrotron with a 3.5 giga electron volt storage ring, 34 beam lines, and 46 experimental stations, serving nearly 40,000 users from over 700 institutions. It is the workhorse of China's photon science ecosystem. And it already has a functioning X-ray interference lithography beamline, the BL08U1B, that is actively being used to pattern nanostructures with sub-100 nanometer resolution. Not in the future. Right now. On a production-capable beamline in an operational facility. 1. The second is the SXFEL, the Shanghai Soft X-ray Free Electron Laser, 532 meters long. The first free electron laser in the world covering the water window, the soft X-ray range between 2.3 and 4.4 nanometers, where water is transparent to X-rays, but carbon and other product. Semiconductor-relevant elements are not. This makes it uniquely capable of probing the electronic and atomic structure of semiconductor materials with a precision and clarity that no other light source can match. Its pulses are 1 billion times brighter than those produced by the SSRF. The third is SHINE, the Shanghai High Repetition Rate XFEL, and Extreme Light Facility, 3,110 meters long. An 8 giga-electron-volt superconducting linear accelerator firing up to 1 million X-ray pulses per second. The largest research infrastructure project in China. When it reached commissioning in 2025, it joined a group of fewer than 5 facilities in the entire world, operating at this class of performance alongside the European XFEL in Germany and LCLS2 at Stanford. It can focus X-ray beams to spots 100 nanometers in diameter with a precision that allows imaging of individual molecules in real time. The fourth is HEPS, the High Energy Photon Source, $665 million. 6 years of construction in Beijing's Huirou Science City, built next to a mountain range specifically chosen because the bedrock provides a stable platform for beams of extraordinary sensitivity. A storage ring 1,360 meters in circumference, longer than 10 city blocks containing 1,776 magnets and over 2,500 power. Supplies. The magnets had to be installed with precision errors no greater than the diameter of a single human hair. Not approximately. Exactly. Because at near light speeds, any small deviation in the electron beam trajectory sends the whole thing off course. 2,500 power supplies, 100,000 control signals. Every one of them monitored in real time from a central control room, where, according to the project director, any small hardware error could affect the trajectory of the electron beam at any moment. It generates X-rays 1 trillion times brighter than the sun. It is the most advanced fourth-generation synchrotron light source in Asia, and when it reached trial operations in late 2025, it became one of only 4 such facilities in the world, alongside Max 4 in Sweden, Sirius in Brazil, and the upgraded European Synchrotron Radiation Facility in France. 4 machines, 1 country, a combined investment running into the billions, and all of them producing light that can probe, image, and potentially pattern matter at scales smaller than 1 nanometer. But here is where the story gets genuinely complicated and genuinely important. What these machines can actually do to chips. You need to hear an honest account of where synchrotron light sources are in the chip manufacturing chain, because the gap between what is being reported and what is actually happening is the most revealing part of this entire story. These facilities are not chip factories. They are not replacing ASML machines tomorrow. HEPS was built primarily as a scientific research platform for materials science, biomedicine, aerospace engineering, and condensed matter physics. The Chinese Academy of Sciences is not claiming these machines will print chips at scale in 2026. That is not what is happening. What is happening is considerably more subtle and considerably more threatening to the Western semiconductor establishment's long-term position. The first and most immediate application is inspection and characterization. Every advanced chip manufactured at the frontier of semiconductor technology has to be verified, its structures measured, its defects identified, its atomic arrangements confirmed before the next process step begins, T 2 nanometers and below. The structures being verified are smaller than the wavelength of any conventional light-based measurement tool can resolve. Synchrotron X-ray imaging can see them. HEPS can focus a hard X-ray beam to a spot smaller than 10 nanometers, smaller than the features on the most advanced chips TSMC currently produces, and image what is inside them non-destructively, layer by layer. With atomic resolution, this capability alone, applied to China's chip development program, gives Chinese engineers a characterization tool that most semiconductor labs in the world do not have access to. The second application is already active. The SSRF has been running X-ray interference lithography experiments since the facility opened. Its BL08U1B beamline uses coherent synchrotron radiation at 13.4 nanometers wavelength, the same wavelength as ASML's EUV light, to pattern nanostructures using interference techniques. It has demonstrated arrays of dots and lines with sub-100 nanometer resolution. It has been used to fabricate magnetic nano-dot arrays, self-assembly templates, and nano-optical components. These are not demonstrations done in isolation. They are published, peer-reviewed results from a running facility serving 40,000 users annually. China has been doing synchrotron-based lithography research for 15 years. The third application is where the frontier of the technology actually sits right now. Chinese scientists and Japanese researchers working in parallel have been testing particle accelerator-based lithography systems for direct semiconductor patterning. As of January 2026, these efforts had already demonstrated 12 nanometer feature printing using X-ray interference techniques. 12 nanometers. On a particle accelerator-derived X-ray source, using single exposure patterning, meaning no multi-step process, no multiple masks, no multi-patterning complexity. Just one exposure, 12 nanometer features. To put that in context, TSMC currently uses double and quadruple EUV patterning to achieve the sub-5 nanometer features in its most advanced chips. Each additional patterning pass adds cost, adds process time, adds yield risk, adds complexity. The entire manufacturing advantage of EUV, the reason ASML's machines are worth $380 million, is that they push patterning to finer resolutions than DUV could achieve. But multi-patterning is the tax you pay for working at the edge of what EUV can do. And the most startling part of the 12 nanometer X-ray result is not the number, it is the implication. EUV lithography requires multiple patterning passes to achieve sub-10 nanometer features each pass, adding cost, time, and yield risk. If X-ray lithography can achieve comparable or better resolution in a single exposure, the economics of the entire approach change, not gradually, fundamentally. But then came the question that no one in the semiconductor industry has fully answered yet. Can you make the machines small enough and cheap enough to actually use in a chip factory? The throughput problem and the people trying to solve it. Here is where honesty demands a clear statement of where the technology currently stands. Synchrotron light sources are enormous. HEPS has a circumference of 1,360 meters. Shine is 3,110 meters long. You cannot fit either of those into a chip fabrication facility. You cannot build one for $40 million the way you might budget a single lithography tool. The industrial-scale photon science megaprojects that China is building are research infrastructure, not fab tools. But this is where the story splits into two parallel tracks running simultaneously. The first track is the one that China's synchrotron megaprojects represent, building the scientific foundation, the materials knowledge, the resist chemistry, the patterning techniques, and the engineering understanding of what X-ray lithography can actually do at the frontier of resolution. Every experiment run on HEPS, every beamline built at SSRF, every femtosecond pulse fired from Shine teaches Chinese engineers things about how X-rays interact with semiconductor materials that cannot be learned any other way. This is the long game, and China has been playing it for 15 years. The second track is where the commercial urgency lives. In the past 2 years, a wave of startups in the United States, China, and Japan have begun building compact, synchrotron-derived X-ray light sources specifically designed for semiconductor lithography machines, small enough to fit in a fabrication facility and cheap enough to compete with ASML on cost. The US company Substrate has demonstrated single-exposure patterning of 12-nanometer line features using X-ray lithography on such a system. Inversion Semiconductor is building a competing machine targeting 10 kilowatts of sub-EUV X-ray output compared to ASML's current 1 kilowatt at a price point estimated at $40 million per tool against ASML's $380 million for a high-NA EUV system. A third company, Xlight, has entered the field from a different angle. And Chinese and Japanese researchers are running their own parallel programs at accelerator facilities, feeding results into domestic equipment development programs with government backing. The economic argument for all of these efforts rests on one calculation. If X-ray lithography tools can deliver sub-2 nanometer single patterning capability at a tenth of the cost of high-NA EUV, and the physics says they should be able to, the entire economic logic of advanced chip manufacturing changes, not at the margins, at the foundation. And here is the connection that makes China's particle accelerator investment strategy coherent rather than disconnected. China's synchrotron megaprojects are not the chip manufacturing tools. They are the research engine that produces the scientific results, the resist chemistry, the patterning demonstrations, the materials characterization data that feeds directly into the development of the compact X-ray lithography tools that will eventually go into factories. HEPS and Shine are to next-generation chip lithography what Bell Labs was to transistors. The facility where the foundational science gets done is not the same as the production line. But without the facility, there is no production line, because there is no science to build it on. And then there is something else happening simultaneously that almost nobody is talking about. The ecosystem China is building around them. Step back from the individual facilities and look at what China has actually assembled. In Shanghai's Jiangjiang Photon Science Cluster, 4 accelerator-based light sources now sit within walking distance of each other: the SSRF, the SXFEL, Shine, and a compact free electron laser test facility. The cluster is deliberately designed so that the same research team can run an experiment on the SSRF in the morning, move to the SXFEL for higher brightness soft X-ray work in the afternoon, and feed results directly into Shine for hard X-ray free electron laser validation in the same week. No other country has this density of complementary photon science capability in a single location focused explicitly on materials and semiconductor applications. In Beijing's Huairu Science City, HEPS sits at the center of a campus that also includes a dedicated platform for advanced photon source technology research and development. 42,640 square meter testing ground for developing and validating new instruments before they are deployed on the main beamlines. This is not an academic afterthought. It is a deliberate pipeline from fundamental science to applied technology, built into the physical architecture of the facility from the start. And feeding both clusters is the Third National Integrated Circuit Fund, 160 billion yuan, targeting every semiconductor equipment choke point simultaneously, including lithography. The explicit government mandate is to develop domestic alternatives to Western-controlled chip-making technology. The synchrotron facilities are the scientific foundation. The equipment fund is the commercial translation layer. And the $43 billion specifically committed to domestic advanced lithography development by Chinese government-linked analysis groups is the production target. This is not a country doing basic science for its own sake. It is a country doing basic science with a very specific industrial endpoint in mind and building the infrastructure, the funding, and the policy architecture to move from one to the other as fast as any country has ever moved in the history of semiconductor technology. The X-ray lithography beamline at the SSRF that has been running for 15 years is not a curiosity. It is 15 years of accumulated knowledge about how X-ray patterning works in practice, knowledge that will flow directly into the compact tools being designed to replace ASML in the fabs of 2035. And none of this required buying a single machine from a Western supplier. The light that changes everything. Come back to that storage ring in Huairu. 1,776 magnets, installed with errors no larger than the width of a human hair. Bending electrons traveling at near the speed of light around a 1,360-meter ring. The light those electrons produce when they turn synchrotron radiation streams off the ring in 14 separate beams, each one directed into an experimental station where Chinese scientists are already working on the science that will define the next generation of chipmaking. The light is 1 trillion times brighter than the sun. Its wavelengths go down to a fraction of a nanometer deep into the hard X-ray range, where features smaller than any transistor currently in production become not just visible but patternable. Think about what this cluster of machines represents as a strategic asset. Export controls work by identifying the specific tools that enable advanced chip manufacturing and restricting access to them. ASML's EUV machines are banned from China because they are the identified choke point. The Dutch government enforces it. The US pressures its allies to enforce it. And for a decade, the strategy held because there was only one path to the most advanced chips, and it ran through ASML, and ASML's machines could be controlled. But synchrotron light sources cannot be export controlled in the same way. They are scientific infrastructure, funded by national governments as public research facilities. The knowledge they generate about how X-rays interact with semiconductor materials, about which resist chemistries enable sub-nanometer patterning, about the engineering requirements for industrial X-ray lithography tools, that knowledge travels through published research, through trained engineers, through the 15-year accumulation of experimental results in facilities that China built with its own money and its own hands. China does not need to buy the next generation of chip-making tools from ASML. It needs to invent them. And it has built in Shanghai and in Beijing the most powerful scientific engine for that invention that currently exists in any country in the world. The machines China is building today are not the chip printers of 2025. They are the laboratories that will produce the science behind the chip printers of 2035. And when those printers arrive compact, powerful, based on X-ray wavelengths that EUV cannot reach, patented in China, manufactured in China, sold by Chinese companies to Chinese fabs, the export control strategy that was supposed to keep China a generation behind in semiconductors will face something it was never designed to stop. Not a Chinese copy of an ASML machine, a Chinese successor to one. Think about how long the West has assumed that the choke points it controls today will remain choke points tomorrow. The assumption embedded in every export restriction, every denied license, every diplomatic call to allied governments, asking them to tighten their own controls, is that the path to advanced chips runs through the tools that already exist and the companies that already make them. That the advantage is locked in, that the gap is structural and permanent. But the light coming out of those beam lines in Huairu and Zhangjiang does not know anything about export controls. It does not need an ASML machine to illuminate a silicon surface with enough precision to write the circuits of the next generation. It just needs the right wavelength. And that wavelength sub-nanometer, generated by electrons traveling at nearly the speed of light around a ring the size of a city block, China is already producing. The light is already on. The science is already running. And in the beam lines of HEPS and SHINE and SSRF and SXFEL, the future of semiconductor manufacturing is being written one X-ray pulse at a time.